All right, what's up, guys? We're back again. Today, we don't have to do an introduction, which is pretty sweet. And so, we're going to try to hop right into it. I know everyone just wants to get out there, get rich, fling a bunch of YOLOs on crypto, or maybe you're an S&P guy. Maybe you like just putting a little money in at a time, watching it grow. Nothing like compounding, baby. So, today we're going to do linear regression, both simple and multiple regression. Both are basically the same concept, and the reason we're going to start with these is because I think it's a great intro in terms of studying relationships between things. If they're linear, there's a lot you can do with them. It's also a good intro to your first kind of machine learning, since a lot of the topics that go into this end up reoccurring over and over again. And it's also mathematically just not that complex. So to start, we did our basic imports. My goal here is to do this pretty much from scratch. I'm just going to use NumPy so that we can vectorize it, make it a little more efficient, do it a little faster. And so I made a normal linear function, our y equals mx plus b, that thing that you learned in high school that when you learned it, you thought this is stupid. Well, it's come back. Here it is. We have our x and our y, which I plotted as just our line. I added a little bit of noise just to show what the idea here is. Basically, if we have data points that we believe have some kind of linear, they have a relationship that's linear, we can use linear regression in order to try to either predict the value, get very close, and as you can see, we have all our points, and we put this nice line right through them. This would be a great predictor. Unfortunately, in the real world, this isn't going to happen that often. We wish it would. We'd all be making a ton of money if this was this easy, but it isn't. And I think some of the most important things when going into linear regression are a couple strict requirements that you need. You'll be able to go read about them on our Medium. You'll see a more detailed explanation of the math and these requirements, but I'll briefly cover them. The first is the linear assumption. So we're assuming that the variables have a linear relationship. Then it's important that we rescale the input data when we use this, because otherwise, let's say you have one feature, one of our x's that we're putting in, and it's just a massive value. It's going to dominate the model and basically make for just a sad, bad time. And maybe you even think it's a good model, and it's not. And that's the worst. Trading already tricks us. We don't need that. The other thing that we're definitely looking for is the features. We don't want the features to be highly correlated. And we'd like to remove as much noise as possible from the input and output variables. And the final thing that we're looking for is generally it's best to have as close to normally distributed input and output data as possible. If you have those things, we can make quite the nice, easy linear regression. So before we jump into building out the class, which shouldn't take much time, it's pretty self-explanatory. Once you look at the math, interpret the math, you're really just putting it to work. Here's our basic y equals mx plus b. We've just used beta instead. We have beta 0, which would be our bias, and we have our one weight associated with x. And then in a multiple linear regression, we just have a bunch of weights and x's. It's the only difference. So you'll see when we go forward and build the class that we just vectorize this. We slap them in vectors, we slap them in matrices, and that's how you do it to make it more efficient. Otherwise, you have to run through for loops, which isn't bad if you're learning, but it helps if you have a large data set to try to vectorize things when you can. So we have our basic linear functions. This is the core building block of linear regression, which makes a little sense since it's in the name. Next, how do we train this? Well, in order to train this, we need the best weights and biases to minimize some cost function. Generally, you're going to see a mean squared error, which is a common linear regression cost function. And this is what it looks like. We're going to take our prediction, y hat, and we're going to see the distance, the squared distance from the actual value. And when we expand it, you can see that it looks like this. And this is where the fun begins, guys. We have some calculus. We got a little Calc 3, I think, where we're finding the weights, which would be our beta 1 to n, and we're finding the bias by taking the partial derivative of this cost function with respect to the weight and bias. Once we know this, we can go ahead and do what's called gradient descent, which is taking these tiny little steps to try to get to that lowest minimum in the cost function. We want to minimize it, and so we're going to take little steps the size of alpha, which is our learning rate, and we're just going to slowly take the previous weight minus alpha times the partial derivative with respect to that weight. When you're choosing a learning rate, you just want to be careful that it's not too small because it'll take forever to converge. And you want to make sure it's not too large because then you're just going to jump right over the minimum. You're going to miss it, and that doesn't do anybody any good. But now we get to do the fun part, which is we're going to build this class. So I already have NumPy imported, which means I can make our class linear regression. And in this class, I really just have to initialize it with a learning rate and then our amount of iterations that we'd like to go through. So this is how many times we're just going to run through an update, and try to get to that minimum. This is basically how many times we're going to let it go through a loop and just keep getting better and better. So the more that you have, the longer it might take. So we'll make our learning rate, and we'll make our iterations. The next thing that I'm going to do after mentioning the mean squared error is it would be nice sometimes to be able to have a function that we can track our loss. And so I'm going to have just a basic list. We're going to append to that list, and we will build our first method, which will make a static method by mean squared error and our prediction. So we have our predicted y, and we have the actual y going into this. All this is going to do is calculate our mean squared error. And we're going to do it with NumPy, because as I explained, we'd like to use NumPy just due to speed. And get the mean. So this will let us just, if we'd like to plot the loss over time, over the iterations, we can do so. We can see how well it's training and if it's doing what we expect it to do. The next part that we're going to do is build the fit. So we have to fit our regression. And so we'll just name it fit. we've got self, we have our x, and we have our y. And so we should probably get how many samples and how many features we have from our x. And so what happens, and how it's pretty easy, we can just do self.m and self.n is equal to x.shape. After that, we're going to initialize our array, the size of the amount of features by weights. So this is just going to be zeros to start off. And we're going to initialize our bias as just 0. I'll make a self.x and a self.y and just assign them to the x and y that we provided. And then this is where our learning, our gradient descent is going to take place. So for I in range, however many iterations we've tossed in there, we're now going to go through and do our gradient descent. Now to clean this up, I'm going to make this a separate function. So we'll do self.update, and then we're just going to return self. So now we have to go make our update function, and self.update is just going to do our gradient descent. So we have self.x, going to predict, which we have to now also make our prediction function, which is easy. So predict self x and return x can be the dot product with the weights plus the bias. So now we make our prediction. Since we have already made our mean squared error, we can get our mean squared error and y prediction, and we can do loss.append mean squared error. So now we can track that through every iteration. We can just see how this evolves over time, see if it's doing its job. We'd like to see it get lower and lower and lower, because we'd like to not have a large mean squared error when we actually deploy one of our models. So now we go back to our partial derivatives, which means we're going to have dw, which is -2 times self.x, and we're going to transpose so that we can do the dot product with self.y and our prediction, just like the formula above. And then m is how many samples we have. And then db will be -2 times mp.sum And so all we did was take the formulas above and we plugged them in. And now we can update with our learning rate times dw, and self.b is self.b. And this also just returns self. So now that we have our update done, we can just make this. And what you may notice now is we're done. We've made our class. We've done everything in our linear regression class. This should work flawlessly. And it was really that simple. We just performed these steps. We just simply got the prediction error. We found the partial derivatives, and then we updated using gradient descent. And so in just a few quick steps, we've implemented a linear regression model, and we can now take any type of data that you guys would like. We can plug it in, play with it, see what the output is, see how it works. And I definitely recommend you trying this out, building it yourself, understanding the mechanics behind what you're using, because as you get deeper into machine learning, it becomes more this mystery box of what's going on behind the scenes, and you'd like to know what's actually happening when you run your algorithm. So many people just load up some of the big packages and modules and plug and chug, and then when they're getting results that they don't understand and using them, it ends up blowing up their account. We don't want to see that. So it's good practice to understand what you're actually doing. And hopefully this was helpful. Hopefully this lets you just see the code, understand some of the math. If you'd like a more detailed explanation, you can head over to our Medium, and we'll have another couple videos coming out this week. So everyone get after it, get coding, make some money, and maybe rip some money into the stock market. Why not? Why not do it with some linear regression? But obviously no financial advice here. This is all just educational. Have a good day coding. We'll see you later.